I'm back. So we were in the middle of this right here when I ran out of time because it only lets me record 15 minutes at a time. So a better way to write this so that it's a little more concise, 10 factorial is 10 times 9 times 8 factorial. And I can divide that by 2 times 1 times 8 factorial. Because after all, 8 factorial is just this piece I canceled out right here. 8 times 7 times 6 times 5, blah, blah, blah. So what I can do is I can then just kill the 8 factorials and get the same thing. And it's much easier to do that way. Like for instance, if I had n plus 1 factorial divided by n factorial, well, n plus 1 factorial is n plus 1 times n factorial, because n factorial would be the product of all the numbers from n down to 1, and then this would be over n factorial, and the n factorials would cancel, and I'd end up with n plus 1. Now, sometimes it's convenient to talk about adding up the first however many terms of a sequence. Like, for instance, if I've got a sequence that represents the amount of money I earn, every day doing something extra, if I'm selling something or doing whatever, then I might want to know my total amount of money, so I might want to have to add up the terms of a sequence. And to do that, we use what's called summation notation. So, to add up the first n terms of a sequence an, we use the following notation. That's read the sum from I equals 1 to n of ai. Here, I is not the imaginary number. I is what's called the index. You can use other letters as well, like J or K. But basically, the way this works is that I starts at its lower limit. Its lower limit is this down here. So 1 is the lower limit. N is the upper limit. And this big symbol you see here, this symbol that looks like this, is a capital sigma. It's a Greek letter. Sigma is like an S for sum. So what happens is, like for instance, if I had the sum from I equals 1 to 5 of ai, well, what that means is that I start at the lower limit and I plug in 1 for I, so this would be a1. And the sigma means I'm adding these together, so plus. Then the index increments by 1, so then it would go to 2. And then plus, and then it would go to 3, and then add, and then it would go to 4, and then add, and then it would go to 5. So that literally means start I at 1, bump it up by 1 every time, and then add these things together. So let's do some practice with that. So let's evaluate something. So the sum from I equals 1 to 6 of I squared plus 1. Well, notice that this would start off with I being 1. So this would be 1 squared plus 1. Plus, then I would become 2. So this would be 2 squared plus 1. Plus, I would be 3. And then I would be 4. And then 5, and then 6, and then that we would stop there because 6 is the upper limit. So that would be 2 plus 5, plus 10, plus 17, plus 26, plus 37, which you can crunch that out, and that comes out to be 97. All right, what if we did this? The sum from k equals 4 to 7 of negative 2 to the kth power minus 5. Well, note that on this one, the lower limit is 4, so you would start adding at 4. So this would be negative 2 to the 4th minus 5 plus negative 2 to the 5th minus 5 plus negative 2 to the 6th minus 5 plus negative 2 to the 7th minus 5. And I calculated this in my notes. This should come out to be negative 100 if you crunch it. The sum from j equals 1 to 5 of 3. Well, note here there's nowhere to plug j in. So when j is 1, you're taking 3, and then when j is 2, you've got 3. And then when j is 3, you've got 3. And when j is 4, you've got 3. And when j is 5, you've got 3. And that equals 15. That's kind of silly because it's a constant. Now, there are different ways that you can write these things. For instance, if I wanted to write the sum from I equals 1 to 5 of I squared, I could also write that as the sum from j equals 2 to 6 of j minus 1 squared. Because with j starting at 2, 2 minus 1 is 1, so that would start essentially at 1 squared and stop at 5 squared. So, I mean, you can write these in different ways, depending. Now, what I'm going to do is I'm going to write out some sequences or some sums, and we're going to write them in sigma notation or summation notation. So let's say I've got 1 plus 8 plus 27 plus ... plus 343. Well, note that this is 1 cubed plus 2 cubed plus 3 cubed plus ... plus 7 cubed. So I'd want to add up all the cubes from 1 to 7. So I could say that this is equal to the sum. I could start at 1, that'd probably be the easiest, from k equals 1. And I can use whatever letter I want. I can use I can use whatever. From 1 to 7 of k cubed. Or if I had this, 1 plus 1/3 plus 1/9 plus 1 over 27 plus ... what? Plus 1 over 3 to the n minus first. So this would be the sum from I equals 1 to n this time, because it doesn't really have a stopping point other than n. And then this could be 1 over 3 to the I minus 1th power. The only other thing I'll say about this summation notation is that if you've got the sum from I equals 1 to n of some constant times a sequence, that's the same thing as factoring out that constant. So adding the sequence together and then multiplying it, it's just like distributing essentially. Also, if I've got the sum from I equals 1 to n of ai plus bi, well, if I'm adding all this stuff together anyway, I might as well add up all the AIs and then add to it all the BIs. And it works the same with minus. It does not work with division for sure, and it does not work with multiplication because of how foiling works. That can get pretty nasty. All right. That is the first extra section.